Okay, let's unpack this. If you're working in data today, you know that the cloud data warehouse wasn't just, an upgrade.
Hmm.
It was a fundamental shift away from the constraints of the past. We're talking about abandoning those old, rigid on-prem systems.
Oh, absolutely. The ones that required that massive upfront investment, complex infrastructure.
And crucially, they just couldn't scale, not for the volume and velocity of data we see today.
It was a necessary evolution, really.
Yeah.
Traditional databases and even some of the early data warehouses, they basically hit an architectural dead end when it came to elasticity.
Right.
You had to make these huge pre-provisioned hardware investments just to handle peak loads that might only happen, 10% of the time.
Such a waste.
The cloud promised this idea of infinite scalability, but the execution needed a platform that was built from the ground up to actually achieve it.
And that platform, the one that really rewrote the rules for this cloud-native world, and the one that pretty much every enterprise data engineer is leveraging today, is Snowflake. So today, we are diving deep. This is a technical exploration of Snowflake's unique, multi-cluster shared data architecture.
And our mission here is to move beyond the marketing slogans. We really want to deliver those aha moments that explain why Snowflake is so often the preferred choice over, say, shared nothing competitors like AWS Redshift or Google BigQuery.
Right.
For you, the data professional listening, this means we're focusing squarely on implementation success. So, how to maximize performance, manage those intense concurrent workloads, and this is the big one, maintain absolutely tight control over your costs.
So let's just jump right in. Let's start with that core architectural choice that makes everything else possible, the decoupling of storage and compute.
This separation it's the linchpin, it's everything. In traditional MPP systems, the shared nothing world, you had these query processing nodes.
Right, and each node had its own local disk attached.
Exactly. Each node had its own slice of the data on its own disk. So if you needed more compute power, you had to add more nodes. But when you added a node, you were also adding storage, and then you had to redistribute all the data across the cluster.
Which was a massive, painful operation.
A huge operation. Scaling was difficult, and performance was always prone to bottlenecks because of resource contention, data shuffling across the network for complex joins. It was a mess.
In essence, you couldn't scale one without scaling the other. If an analyst needed intense compute for a few hours, you were forced to over-provision the storage layer permanently.
Right, leading to massive inefficiencies.
Mm-hmm.
Snowflake it flips this model entirely. Storage and compute are completely independent. The data resides permanently in cloud storage. We can call that the foundation layer.
Okay.
And the compute power comes from these independent ephemeral virtual warehouses, or VWs.
And that decoupling, that lets us scale those VWs up or down based purely on what we need right now without ever touching or reorganizing the data underneath.
Exactly.
Yeah.
And crucially, this is what eliminates the performance bottleneck you see with concurrent varied workloads.
So if one team is running a massive resource-intensive ETL job, and another team is running some lightweight dashboard queries, they can each have their own dedicated, isolated compute resources. No fighting over CPU.
That isolation is key. Let's break down the 3 distinct layers to really see how this separation is orchestrated.
Okay, let's do it. Starting at the top, the master controller, the shared brain.
The cloud services layer.
The cloud services layer is the heart of Snowflake.
Yeah.
It's interesting because unlike the compute layer, which is user-specific, the services layer is heavily multi-tenant. It's long-lived, and it's shared across many, many users and accounts.
And that design choice is what gives you the economies of scale. Right?
Exactly. It handles all the complexity that would otherwise fall onto the engineer.
So what are its core responsibilities? I mean, I know it handles the obvious stuff like authentication, but what about the deep operational management? So it manages the entire operation: authentication, access control, infrastructure management, so just spinning VWs up and down. It has the query optimizer, the transaction manager. But maybe its most vital and often least understood component is the metadata storage. This metadata, catalog objects, statistics, table structures, and really importantly, the physical mapping of logical tables to actual files in S3.
Yes.
All of that is stored in a scalable transactional key value store.
Why is calling it a transactional key value store so important for an engineer to understand?
Because it's what ensures global consistency. Imagine you're running a complex DDL operation, like adding a column, and at the exact same time, a huge ETL job is running DML, modifying data in that same table. This transactional store guarantees atomicity and serialization across all of those operations, no matter which virtual warehouse kicked them off.
So DML and DDL operations are non-blocking.
They're non-blocking, and they're consistent across the whole platform. That's critical for any kind of continuous integration pipeline. It's the reason Snowflake can handle massive concurrency without all the locking or blocking issues you see in older architectures.
That's the brain. So now let's talk about the muscle. The virtual warehouses layer. The VWs.
The VWs are where the actual query execution happens. They're basically clusters of worker nodes, EC2 instances typically, but they're presented to you, the user, through those easy t-shirt sizes.
Right. X small, small, medium, all the way up to XX large.
And that abstraction is incredibly clever because it shields you from all the underlying cloud hardware details. It lets Snowflake optimize the platform continually without you having to retune your workloads.
And like we said, these are ephemeral. They're dedicated to the workload. X small costs 1 credit per hour, small is 2, medium is 4, and it just doubles from there.
Precisely. They are independent compute clusters. So if you have 3 different teams running 3 different reports at the same moment,
they can use 3 separate VWs.
Exactly. And that absolute isolation is why concurrency is so effective on Snowflake. A sudden spike in complexity or data volume on one VW does not degrade performance on the others.
Okay, but if they're ephemeral and they're independent, how do they maximize efficiency? They must be using caching, right? If I run the same query twice, I don't want to re-download all the data blocks from S3.
Absolutely. VWs use 2 levels of caching. First, there's the result cache, which is actually managed by the cloud services layer.
And that just stores the result set of a query if the exact same query is run again.
Right, assuming the underlying data hasn't changed. But more importantly for performance, the VWs themselves maintain a local disk cache.
Tell us about that local cache.
So this is a cache on the worker nodes themselves. When a VW executes a query, it pulls down the relevant micropartitions, the physical files, from cloud storage onto its local SSDs. This cache stores the file headers and, critically, only the specific columnar data that was accessed by the query. It operates on an LRU, at least recently used, policy.
So if the next query hits the same data block, it's served locally from that superfast SSD.
And that accelerates performance significantly.
Okay, so how does the query optimizer make that cache even smarter? How does it make sure that concurrent queries hitting similar data can actually benefit from what's already loaded?
That's where consistent hashing comes in. The query optimizer uses consistent hashing to assign the input files, those micropartitions, to specific worker nodes inside the virtual warehouse cluster.
So if multiple queries running on the same VW need the same files,
They tend to land on the same worker nodes. This boosts the local disk cache hit rate, maximizing the benefit of that expensive I/O operation only happening once.
Okay, let's move to the bottom layer, the data storage layer, the foundation. This is where our actual bytes live.
Right, so the data is stored in an optimized, compressed, columnar format in whatever cloud provider's storage layer you chose, SS3, Azure Blob, and so on. The real genius here is in the micropartitions. Data is horizontally partitioned into these contiguous storage units. They are typically large, immutable files.
We hear that term micropartition all the time. What does it actually contain beyond just the data itself?
So each micropartition, which might hold, say, 50 to 500 megabytes of uncompressed data, contains a ton of metadata that's managed entirely by Snowflake.
Okay.
This metadata includes the range of values for every single column in that partition, the number of unique values, clustering information. And this is all crucial for the performance technique known as pruning.
And pruning just means skipping data we don't need to read.
Precisely. So if your query has a predicate, say where dated 2023-10-01, the cloud services layer checks the metadata store before it even sends the query to the virtual warehouse.
Right.
It looks at the value ranges stored for that dated column in every single micropartition. If a partition's metadata shows its highest date is September 2023, the optimizer just prunes it.
It just drops it from the scan list.
The VW never even requests the file.
Yeah.
This drastically accelerates query times on really large tables by minimizing the amount of data you have to read from cold storage.
So we've really shifted from a world of manual tuning to one of automatic elasticity. When we compare this to the legacy systems, what does this actually mean for the hands-on data engineer on a Tuesday morning?
It means we spend way less time being database administrators and more time actually engineering.
Amen to that.
Legacy DWs relied so heavily on manual intervention. creating and managing indexes, figuring out the perfect partition scheme, constantly tuning queries based on execution plans. And if your data volume changed, your partitions were suddenly suboptimal.
And the scaling costs were astronomical.
They were fixed and they were slow. If you needed more power, you had to go buy a bigger box. Snowflake, on the other hand, it offers this elasticity. We can scale instantly from an X small VW to an X large, and we can use automatic scaling to handle sudden bursts of data processing, and we only pay for the seconds we actually use.
For a modern ELT pipeline, that is the difference between a load job taking 10 hours on a fixed-size cluster.
And 10 minutes on a scaled-up, optimized VW. It's a different world.
Okay, that's the architectural foundation. Now let's drill into the features that are built on top of it that directly address some of the most common data engineering pain points.
Let's do it.
Let's start with the reality of modern data. It's messy. We're not just dealing with perfectly structured SQL tables anymore. We're getting feeds of JSON, XML, Avro, and dealing with this semi-structured data used to be a nightmare, right? It required these complex parsing layers before you could even think about loading it.
Oh, yeah. Snowflake revolutionized this by introducing the variant data type. It lets you load JSON or XML or Avro data directly into a table column without having to predefine a strict schema.
It gives you the flexibility of a schemaless system.
Exactly.
But the age-old problem with schemaless systems like a MongoDB or Cassandra is that you always trade performance for that flexibility. So how does Snowflake give us both the flexibility and the speed of a columnar database?
They use this novel automated approach. It involves type inference and a specific storage technique you can call PAX or hybrid columnar storage for that semi-structured data.
Okay, what does that mean in practice?
When you load semi-structured data into a variant column, Snowflake doesn't just store the serialized JSON string as a big blob of text.
Right.
It automatically detects the inherent structure within that JSON, the keys, and their corresponding values.
And how does that affect the actual storage on disk?
Well, instead of storing the full JSON string over and over again, Snowflake extracts those individual attributes, say user ID or purchase price, and it stores them internally in a column-oriented format, very similar to how it stores regular relational data.
So it's a hybrid approach.
It is. It means when you run a query that references a specific JSON key, like data.purchaseprice, the engine is actually accessing a virtual column that behaves exactly like a native columnar structure.
So you get huge compression benefits and massive performance gains because the engine can prune based on the values in those internal virtual columns.
Right. It avoids having to parse the entire JSON object on every single query.
That is the ultimate best of both worlds solution. You get the flexibility of schema evolution with the query speed you need for large-scale analytics. Okay, now let's talk about development agility. A huge pain point for engineering teams is just spinning up test environments that actually mirror production.
Right.
This used to involve these complex, super time-consuming ETL jobs to copy or mask production data.
That whole process is now obsolete thanks to zero-copy cloning. I mean, this feature is an absolute game changer for CI/CD pipelines. It lets you create instant writable copies of tables, schemas, or even entire databases.
And the critical aha moment here is that when you clone something, you don't actually copy any data, at least not initially.
Correct. The derived copy is purely a metadata operation. The new object simply points to the same underlying micropartitions as the original object in the storage layer.
So you incur zero immediate storage costs.
Zero. And the clone happens instantaneously. Storage consumption only starts when that cloned environment begins writing or updating data, creating new micropartitions that are specific to that copy.
That just fundamentally changes how you do test data setup.
It does. It lets engineers spin up full multi-terabyte production replicas for testing in seconds, not hours or days. Seconds.
And what if an engineer makes a mistake? Or a really complex ETL job fails catastrophically?
Then we use time travel. This functions as a transparent, system-wide undo button.
Okay.
Snowflake automatically retains historical versions of your data, allowing you to access previous states using AT or before clauses right in your SQL. For enterprise versions, this retention can be up to 90 days.
I often hear engineers confusing time travel with standard backups. How is it different?
It's integrated and it's continuous.
Yeah.
Standard backups are just point-in-time snapshots that require an explicit, often slow restoration process. Time travel's always on. You can use it to query data as it existed an hour ago, run analytics on past states, or, and this is critical use, the UN draw P command.
The ultimate lifesaver.
It really is.
Mhm.
If you accidentally drop a mass pick table or a schema, or even an entire database, as long as the data retention period hasn't expired, UData recovers the object instantly and atomically just by using the metadata stored in the cloud services layer.
Okay, security. It's non-negotiable in the enterprise, yet we rarely have to touch key management in Snowflake. It feels very transparent. So tell us how Snowflake achieves enterprise-grade security completely behind the scenes.
Well, it starts with robust encryption. Everything is protected using strong AES 256-bit encryption at rest. And the mechanism relies on a hierarchical key model. And this is where the architecture really integrates with the physical security of the cloud environment.
And that hierarchy is rooted in Cloud HSM. Why is that important?
Cloud HSM provides a tamper-proof hardware device for generating and storing the highest level keys, the root keys. And its significance is really about compliance, specifically FIPS 142 Level 3 compliance. For highly regulated industries like banking or healthcare, having this hardware-backed root of trust is essential. Yet the Snowflake engineer never has to manage the certificate process.
So we have the root key, the account key, the table key, and the file key, and each one encrypts the layer below it. This hierarchy is powerful, but key management isn't a one-time setup. It needs rotation.
Exactly. Key management compliance demands a lifecycle process. Snowflake handles two automated processes transparently to meet NIST standards: key rotation and rekeying.
Can you explain the practical difference between those two?
Sure, key rotation creates a new version of the existing keys at regular intervals, say monthly. When a rotation happens, only newly written data or newly encrypted child keys will use the latest active key version.
So the old versions remain usable for decryption, but they're retired for encryption.
Exactly. It's an efficient way to limit the risk exposure of any single key version.
Okay, and rekeying, that sounds like a much bigger operation.
It is. Rekeying is the process of re-encrypting the actual data with a new active key. This usually happens on a longer cycle, maybe annually.
Hmm.
It's a massive background process that leverages dedicated worker nodes, completely separate from your virtual warehouses, to rewrite and re-encrypt the underlying micropartitions. And crucially, you, the user, experience no downtime, no performance impact, and zero configuration.
Beyond this foundational encryption, engineers need granular control over who sees what data. And this brings us to governance features like role-based access control, dynamic data masking, and row access policies.
Right, so RBAC is pretty standard for access to tables or schemas.
Mhm.
But when you have sensitive PII that exists in certain columns, that's when you need dynamic data masking, or DMM.
Okay.
DMM lets you apply a policy, which is basically a SQL expression, to a column. This policy executes at query time. So for instance, if an analyst with a junior role queries a social security number column, the policy might return only the last 4 digits.
But a senior role might see the full number.
Exactly. The underlying data is still there in plain text, but the policy masks the output based on the user's role and context.
And row access policies handle the horizontal filtering.
That's row access policies, or RAP. This determines which rows are returned. For example, in a multinational company, a RAP might restrict an analyst to only seeing customer data from their own country or region.
So the query executes select from table.
But the policy automatically injects an invisible where clause based on the user's attributes, ensuring they only see the records they're authorized to see. This combination gives you really comprehensive logical access control, which is vital for regulatory compliance.
Finally, let's look at one of the most transformative features for large enterprises and data vendors: secure data sharing. In the past, sharing large data sets meant complex data exports, FTPs, setting up dedicated replication pipelines.
All of which duplicated storage costs. It was a nightmare.
Hmm.
Secure data sharing leverages that same separation of storage and compute model we talked about. You can share selected objects tables, secure views, materialized views, UDFs with other Snowflake accounts, whether they're your internal business units or external partners.
And the magic is that the data is never copied.
Correct. The data remains stored once, in the provider's account. The sharing mechanism works purely by sharing the metadata via the cloud services layer. The consumer account just gets read-only access to the provider's micropartitions.
So because they're only accessing the metadata pointer, the shared data consumes zero storage in the consumer account.
Zero. That's right.
Walk us through the mechanics. How do you set up a share?
It's actually really straightforward. As the provider, you create a share object. You then grant usage on the necessary database and schema, and you grant select access on the objects you want to expose.
And then you just add the consumer account.
You add their account ID to the share. The consumer then creates a database on their side that just points to that share. And importantly, you can even create a specialized reader account for external partners who don't have a paid Snowflake account, giving them secure, limited access without any cost to them.
It really democratizes data access.
It does, without compromising the security or storage efficiency of the provider.
Okay, so now we shift from architecture and features to the practical application. How do we as data engineers take these capabilities and build a robust, scalable pipeline? This always starts with structure.
It does. Modern data engineering really demands a layered approach. We use schemas to enforce the separation of concerns, improve data quality, and allow users to consume data that's appropriate for their specific needs. This moves us toward that medallion architecture concept, which you can often boil down to three main zones.
Let's define those three layers.
So we start with the land or source or raw schema. This is pure ingestion. We land the raw data exactly as it arrives, with minimal or no transformation, just to preserve the fidelity of the source.
Got it. Layer one.
Next is the clean or curated schema. This is where your basic standardized curation happens. Deduplication, harmonizing formats, fixing known data quality issues, applying basic business logic.
And then finally,
the consumption schema. This is your analytics-ready layer. It typically involves dimensional modeling, a star schema or a Snowflake schema that's optimized for reporting and analysis via tools like Tableau or Power BI.
let's use that Cricket Analytics project as our grounding example. We're receiving match details, player stats, and delivery data, maybe in a mix of structured and semi-structured formats.
Okay, in that scenario, our raw JSON data on match deliveries lands directly in the land schema, probably using that variant type we discussed. We then process that raw data in the clean layer. This would involve structuring the JSON into clean, normalized tables for, say, match details and player information, running basic checks for nulls or duplicates.
And this culminates in the consumption layer.
Right, where we model the data. We build out our dimension tables like dim referee, dim team, dim date, and one or more fact tables like fact delivery events, all optimized for those fast analytical queries.
Okay, so the shift to LT extract, load, transform, is fundamental to Snowflake. We load first, then we transform using the platform's own compute power. So how do we get the data into that initial land schema?
For massive historical data sets, we use bulk loading via the copy to command. This command is highly optimized for parallelism and can load files from stage locations, either Snowflake's internal stages or external cloud stages like S3 buckets.
So the engineer just has to specify the file format and the target table.
That's it.
That handles bulk. But modern data ingestion is often a continuous flow. We need near real-time ingestion capabilities.
And that's where Snowpipe comes in. Snowpipe is Snowflake's continuous data ingestion service. It enables auto-ingestion. So as soon as new data lands in your external cloud storage, say S3, a notification event triggers Snowpipe.
So the data engineer isn't constantly polling the storage location.
No polling. Snowpipe is event-driven. It uses the copy into statement internally, but the execution is managed and optimized by Snowflake. It maintains a state file. It tracks which files have already been loaded. It ensures idempotency.
And that's crucial for microbatch or near real-time ingestion.
It is. It allows data to be available for query within minutes of being created without the engineer having to manually orchestrate that loading process. And importantly, Snowpipe pricing is based on the compute time needed for the load, which often results in significant cost savings over having a VW running 247 just waiting for files.
Okay, so once the raw data is loaded, we need a reliable way to orchestrate the movement and transformation between the layers, from land to clean to consumption, and especially handling changes, not just full reloads. This demands change data capture, or CDC.
This is where Snowflake streams become indispensable. You just can't build a modern pipeline without them. Streams track DML changes, so inserts, updates, or deletes that are made to a source table. A stream acts like a delta pointer. It doesn't hold the change data itself. It just records the offset position of where changes have occurred.
So when a transformation job reads that stream, it only processes the changes since the last time it checked.
Exactly. It prevents these massive redundant data scans. Streams only show you the delta. Once the stream is consumed by a transformation, the offset pointer advances. If no changes have occurred, the stream is empty, and the dependent job doesn't run, which saves compute credits.
And how do we automate the execution of the SQL transformation that consumes these streams?
We use tasks. Tasks automate the execution of SQL statements or stored procedures on a schedule, maybe every minute or every hour. Tasks are really the orchestration layer inside Snowflake. For complex pipelines, we build these task graphs, where one task successfully completing triggers the next dependent task.
The critical efficiency game here is tying the task execution directly to the streams.
It is. You don't want the task running if there's no new data to process. So we use the conditional clause when system stream has data on the associated stream. If the stream is empty, the task just skips its execution.
Again, ensuring we only pay for compute when there's actual work to do.
Precisely.
Let's apply this directly to one of the most challenging transformations in dimensional modeling,
Yeah.
implementing a slowly changing dimension, or SCD, type 2. This is vital in any banking data stack or logistics pipeline where you need to track history.
Oh yeah, customer address history, product status changes. SDD Type 2 is a classic problem. It requires tracking history by creating a new dimension record for any change rather than just updating the old record. So you're managing validity timestamps, valid from, valid to.
Walk us through the practical implementation using streams and the merge statement.
Okay, so in our pipeline, we have a source table, let's say customer source, and a target dimension table, dim customer. We first create a stream on that customer source table. Let's call it customer stream. The downstream transformation task then runs a single powerful merge statement where the customer stream is the source.
What are the two main steps inside that merge operation?
So first, you handle the changes to existing records. If the stream detects a key that already exists in the dimension table but has different attributes, like the customer's address changed, the merge statement does not update that record. Instead, it runs an update only on the existing dimension record to set its valid to timestamp to the current time.
So it effectively closes out its validity window.
Exactly. You've archived it.
Yeah.
And the second step is to insert the new history.
Right.
So the merge then executes a second insert operation using the data from the stream to create a brand new record for that customer. This new record has the updated address, a valid from timestamp set to now, and a null or future valid to date, marking it as the current active record.
And that's one atomic operation?
One atomic operation handles both the historical archiving and the current record creation seamlessly.
And this is exactly what tools like DBT leverage when they're using their snapshot feature, isn't it?
Precisely. DBT snapshots just automate this entire SCD Type 2 logic. They rely heavily on the power of Snowflake's merge capabilities. DBT manages the boilerplate SQL, it tracks its changes, sets the necessary metadata columns like dbt valided from and dbt valado, and it runs these models directly inside your Snowflake environment.
Let's talk about quality control. Standard data quality checks like, checking for nulls or duplicates are essential, but for complex, large-scale data, we need more advanced profiling.
Absolutely. Data quality has moved beyond just basic checks into statistical analysis, often leveraging tools like data wash or custom Python code that's running on Snowpark.
And Snowpark lets engineers run Python or Java or Scala code directly on Snowflake's virtual warehouses.
Right, bringing the processing to the data.
So if we look past the standard checks, like the null count check, which just flags a column if the percentage of nulls goes over some threshold, what are the advanced checks that genuinely catch issues that traditional ETL monitoring would miss?
For me, I focus on distributional and correlational checks. Take the outlier detector. Instead of setting some manual maximum value, this check learns the acceptable range based on the data's historical distribution.
So if a price column usually ranges between $10 and $100,
and suddenly 0.01% of the records show a price of $10,000, the outlier detector flags that atypical behavior immediately.
I can immediately think of a project where a small bug in a source system led to erroneous transaction amounts. This would have caught it in a second.
Absolutely. Then there's the correlation check. This flags atypical relationships between two different columns.
Okay, an example.
In an HR dataset, you typically see a correlation where salary increases with years of experience. The correlation check will flag a small percentage of records where a brand new hire has a suspiciously high salary compared to the dataset's standard deviation.
That's effectively monitoring the physics of your data.
Yes. And we also use the distribution check. This compares the current data's distribution against its historical pattern, often using statistical tests like the Kolmogorov-Smirnov test. If the shape of the data, not just the mean or max, subtly changes, it can flag a subtle shift that indicates a process error or a change in the source system.
Interesting.
And finally, there's the freshness check, which just monitors the frequency and volume of new data. If a feed that normally delivers 10,000 rows every 5 minutes suddenly delivers only 100, the check flags that deviation, alerting us to a potential upstream failure.
Okay, we've established that performance is maximized by architectural separation and caching. But the data engineer still has significant control over optimizing their workload. Let's look at how we maximize query performance in practice.
Well, the foundational optimization is the automatic work that's done by the query optimizer, leveraging that micropartition metadata we talked about.
Right, that pruning technique is always running.
It's always running. And the engine is always distributing query processing across the VW worker nodes to maximize parallelization.
But the engineer has to provide explicit guidance sometimes, especially for very large, highly transactional tables. And this is where automatic clustering and the clustering key come in.
That's right. For tables that are getting updated a lot, their natural ordering, the order in which the data was loaded, it becomes suboptimal over time. Queries start scanning too many micropartitions. So Snowflake offers automatic clustering to continually monitor access patterns and reorganize the data physically.
And how does the engineer guide this process?
The data engineer explicitly designates a clustering key. This is a subset of columns that are used most frequently in where clauses and joins. Snowflake then works in the background to co-locate data based on those key values within the micropartitions.
So by co-locating that data, you improve the effectiveness of the pruning mechanism significantly.
Massively. If your clustering key is effective, 99% of your queries will only need to scan a minimal number of micropartitions.
That feels like the cloud-native replacement for manual indexing and partitioning.
It is, but it's managed automatically. Unlike manually partitioning a table, the engineer doesn't have to worry about defining partition boundaries. Snowflake handles all the underlying complexity, and you just pay credits for the compute time used for that background clustering process.
And for recurring aggregated queries, analysts are always relying on materialized views, or MVs.
MVs are essential for high-throughput reporting. An MV pre-computes the results of an expensive query, often aggregating or joining large tables, and it stores that result set in a dedicated cache. They're also transparently maintained by Snowflake.
So when the base table data changes, the MV automatically refreshes.
It does.
But if we already have that powerful result cache, why do we still need materialized views?
Because the result cache only works if the query is absolutely identical. MVs are used when the query is complex, involves significant aggregation, and needs to be served fast, even if the user's query is slightly different or uses a subset of the MV.
Okay, but there's a trade-off.
The trade-off is that MVs occupy storage, unlike standard views. So engineers need to be strategic about which aggregations are truly necessary to materialize versus which ones can just rely on standard caching and automatic clustering.
This brings us to the biggest challenge for many engineers operating in the cloud: cost control. Since compute and storage are decoupled and the majority of the costs, we're talking 70 to 80%, comes from virtual warehouse usage, managing those VW credits is paramount.
Paying per second for compute is amazing for agility, but it definitely introduces a management overhead. The core strategy is managing the VW lifecycle, making sure they suspend when they're idle and that they're appropriately sized for the workload.
Right. An oversized VW on a small job is wasted money. An undersized VW on a massive job means slow execution, which also costs more in total time.
Exactly.
I want to challenge that concept of fine-tuning t-shirt sizes, though. Doesn't the complexity of constantly choosing the right size, X, small, small, medium, introduce significant management overhead compared to competitors with simpler, maybe fixed-rate consumption models?
It absolutely can if you're doing it manually. The solution isn't manual tuning, it's applying predictive analytics and machine learning to the problem.
Okay.
Engineers are now implementing ML models to forecast resource utilization based on historical query patterns, seasonality, and data arrival volume.
How does that prediction translate into actual cost savings?
The ML models can tell us, for instance, that between 2 a.m. and 4 a.m., the ETL workload needs the parallelization of a medium VW, but for the rest of the day, an X small is perfectly sufficient for dashboard queries.
So you can automate the scaling policy.
You automate it, you tailor the optimization techniques, dynamically scaling up just before a predicted peak and scaling down immediately after. Some studies have shown that just right sizing and ensuring proper suspension and resumption settings can get you 20 to 40% cost reductions right out of the gate.
It turns cost management into an engineering problem, not an accounting one.
That's a great way to put it. The core action for the engineer is still utilizing that elasticity feature effectively. If your task graph runs a complex merge statement, scale up to a large VW to finish the job in 30 seconds. Pay for 30 seconds of large credits. If you use an XMall to run the same job for 10 minutes, you might pay fewer credits per minute, but the total elapsed time and potentially the total cost is higher. Plus, you delay everything downstream.
So speed often equals cost savings in Snowflake.
It really does.
Finally, Snowflake isn't sitting still. It's expanding rapidly from being just a cloud warehouse to becoming this unified data platform. Let's look at how its architecture supports adjacent technologies like ML feature stores.
The architecture is perfectly suited for machine learning needs. Since storage and compute are decoupled, Snowflake supports seamless ML feature engineering, storage, and serving.
Okay.
You can run your feature calculations using Snowpark Python, store the resulting features, and serve them at high speed. The platform's ability to handle highly variable loads consistently means engineers often don't need to build separate, dedicated feature store solutions.
Which simplifies the entire MLOps pipeline dramatically.
Massive.
We're also seeing a major industry push toward open standards, specifically around storing data outside of proprietary formats. And Snowflake is addressing this with Apache Iceberg.
The move to open pipelines is critical for multi-cloud and multi-engine flexibility. Snowflake now supports storing data in Apache Iceberg tables with open catalog support. And Iceberg is rapidly becoming the industry standard for large analytical data lakes.
So what does Iceberg offer that's fundamentally better than standard file formats?
Iceberg provides these key capabilities that make data lakes much more robust. Things like schema evolution. You can change the schema without complex manual rewrites.
Right.
Partition evolution, so you can change how the data is partitioned without breaking old query plans.
Yeah.
And transactional consistency. By supporting Iceberg natively, Snowflake is ensuring that the data produced within its platform can be consumed by other open engines like Spark or Trino, promoting true data portability.
And for the engineers' day-to-day work, how is the development environment maturing to support these complex pipelines?
The development interfaces have matured significantly. I mean, we have native SQL development through Snowsight worksheets and the command line interface, SnowSQL. But for professional engineers building robust pipelines, the key is the integration with workspaces.
And workspaces offer the full IDE experience, right?
Yes. Workspaces provide an advanced integrated development environment directly within Snowsight, and they support version control. The integration with Git is essential for robust DevOps and CI/CD pipelines. Engineers can edit, version, and collaborate on their SQL, Python, or JavaScript files, all backed by a Git repository, which streamlines deployment and rollback procedures. It fully formalizes the process of taking code from development, testing it with cloned environments, and promoting it to production using tasks and streams.
Okay, here's where it gets really interesting. We've covered how Snowflake's unique separation of storage and compute, its centralized metadata management, and its automatic optimization features. They fundamentally change how data professionals approach scalability, governance, and complex transformations like that SCD Type 2 logic. It really shifts the burden of infrastructure management away from the engineer.
That's the core takeaway. The platform offers this unique balance. Automatic optimization is always running in the background, but the engineer retains explicit architectural control like choosing the right t-shirt size and defining the clustering key to ensure performance targets are met, cost is contained, and millions of transactions per day are processed efficiently.
So this deep dive really shows that Snowflake isn't just a database. It's an ecosystem designed for high concurrency, complex ELT workloads, and it's ready to handle the scale of open data formats like Iceberg.
And if we connect this to the bigger picture, given the platform's multi-cloud architecture and the transparency it provides on complex operations like key management and security, the biggest challenge moving forward isn't scaling the technology. It's transitioning to a truly self-service model. That means providing tools and interfaces, maybe through highly abstracted Snowpark functions, where every user can leverage this immense scale and complexity from data science to business analytics without needing to understand the underlying infrastructure. And this raises an important question for all of us. In a world of virtually infinite scale, how much of the underlying engineering complexity must remain visible to truly govern the quality and access of the data?
That is a fantastic thought to end on. And it leads me to my final question. Why did the data engineer break up with the data warehouse?
Why?
Because it kept trying to update their relationship status without setting a proper DBT value timestamp.